You know, I actually don't think it tastes the most. As long as I stand on the full push or two, I think. Okay. Yeah, that
All right.
was
Welcome. Happy Tuesday. Oh, no, not Tuesday. That's when all my other classes are. Happy Monday. Uh, Welcome. Hope you're having a good day so far. Things we've got going on today. We have our last chapter one, prepare for calculus section. And then we get into limits with chapter two on Wednesday. So you'll have your weekly written homework two due on Friday. That will be inverses, logs and exponents of today, and then the start on limits that we'll talk about Wednesday. That we do Friday. You have the inverse post-class activity that's due by the end of today. Then you'll have one on logarithms or exponentials due today. I mean, not due today, assigned today, due Wednesday. Wednesday, something on limits, and then Friday, something on limits as well. And then also I've added to it so that I actually keep mentioning it. We discussed it on Friday. There's that big set of practice problems. Those are due the date of the first exam. I mean, I recognize the dislike, but there's always that method to the madness. And I want you all to have lots and lots of practice because can't learn math without practicing it. Um, and then written homework three, I will get written this week and posted. And that will be the last written homework before the first exam, I believe, because our exam is coming up the 9th. And next week we're in February, so yeah, I'll be coming up soon. So keep talking about that. So any questions on announcement stuff as we're getting going? All right. I also, you may have seen, had the homework scores put in this morning. So I have those to hand back. Christian, Daniel, Nathan, yeah.
thank you.
Give you guys a little bit of time to look through those. Tried to give some guidance on different things where points were taken, whether it be, hey, you missed this part of the problem, or here's the mistake you made with the circle. So I'll give you guys some time to look through it and ask if there's any like problem questions that you may want looked at. Like how were we supposed to do a certain problem? Any questions looking through? A minute or two more. right. Oh, yes,
I guess for number 9,
9. Okay.
what the solution would be, because it has to. I didn't.
Yeah, so most people got, if that was the solve the trig.
Yeah.
Yeah. So several people left off one of them. And that was, and I tried to circle what that last one was. So let me find that homework problem so that we can look at that. Yeah. Homework 1, 201. Should be us. That's the PDF. Okay. So got all of this worked down. I have not unfrozen my screen yet. There we go. So number 9, solve the equation for theta, where 0 is less than theta is less than 2 pi, with each of those less thans having a less than or equal to. So, we move everything to one side and have 2 cosine squared theta minus cosine theta minus 1 equals 0. And then that factors into, what did that, most everyone had that. What did that factor into? Should have had a factor into it. Cosine theta minus 1 to cosine theta plus 1. So then we set equal of cosine theta minus 1 equals 0 to cosine theta plus 1 equals 0. And we get cosine theta equals 1, or cosine theta equals -1/2. So this one, cosine theta equals -1/2. So the x coordinate is a -1/2. So on our unit circle, be this angle and that whole angle there. And where x is a half goes with 2 pi, or yeah, 2 pi over 3 and 4 pi over 3 if we use our unit circle or reference angles. You should get those two. This is the one where there were a bunch of a missed angle. Most recognized, hey, that point's right here where the angle is 0. But this part is what I circled on most anyone who had that, or I wrote it in. It could also be all the way around by that less than or equal to. So the one missed by most was that theta also could be 2 pi. If there wasn't the little bar, these 3 would have been the correct, but because of that little equal to, it could have been 2 pi as well. So paying attention to what domain we're given does matter. Any others or any follow-up on that? Okay. Erase this so that if I ever pull this up again, it doesn't have that written on it, because I will forget. All right. Nothing else. We will get into 1.6. So 1.6 is reviewing exponentials and logarithms. With the first, the properties of exponents, which hopefully you've seen these rules at some point. But first property of exponents, anything to the 0 power. With a slight caveat, but not one we're going to worry about right now. Anything to the 0 power is 1. If I have the same base, a to the x, a to the y, we can add those exponents together. The reason being for this, thinking about what exponents mean. Say I have 2 cubed times 2 to the 5th. That means I have 2 times 2 times 2 times, I'm not going to actually say this one, too many 2's. But if I now count how many 2's I have 3 2's plus 5 2's, or 2 to the 8th. So this rule is coming from, hey, if I actually know what exponents mean of repeat multiplication, I can look at how many groups I have and add those together. Rule 3 is that power to a power, you multiply those two powers together. Again, quick reasoning. Say I have 2 cubed squared. This means I have 2 times 2 times 2 times 2 times 2 times 2. I have 2 sets of 3 2's. 2 times 3 is 6. So again, in those multiplication ideas of what exponentials mean, we have these given rules. 4 is a rearrangement. So say I have xy cubed. That means I have x times y times x times y times x times y. I can just rearrange it so all my x's together, I have 3 of those. All my y's are together, I have 3 of those. So I can distribute an exponent over multiplication. I cannot do it over addition. You will notice there is no rule here about the bases being added or subtracted, meaning the lower part being added or subtracted. It's only ever the exponents that get added or subtracted. So, note. When it comes to how do exponents work, they're not ever going to be over that addition or subtraction, or else it's going to be really funky. Rule 5 is just the division form of it, where if I am dividing a bunch of things, say, going back to my 2's, I have 2 cubed over 2 squared, very basic number of things, 2 times 2 times 2 over 2 times 2. Everything cancels except for a 2 to the first that's left. And 3 minus 2 is 1. That's what rule 5 is saying. Rule 6 is rule 4, but with division. And rule 7, the one that throws us off the most based on what we just talked about on Friday. A negative exponent moves that thing where it is in the fraction. So 2 to the negative 1 equals 1 over 2. If I had 2/3 and the 3 was to the negative 2, this would mean 2 times 3 times 3, or 18. I don't know why I solved that one and not any of the others. But a negative moves where something is in the fraction. If I have a whole fraction to a negative exponent, like 2/3, it flips the whole fraction. but it's paying attention to where is the negative. If it's on the whole fraction, it flips the whole fraction. If it's only on the denominator, it only moves the denominator. If it's only on the numerator, it only moves the numerator. And the distinction I tried to make on Friday, it's a very generalized distinction, but it is one nonetheless. If I have a number to a negative exponent, that is reciprocal. If I have a function with a negative exponent, that means the inverse function. So things you will not, well, things we see, sine inverse means the inverse function of sine because it's on a function. We have a reciprocal of sine. The reciprocal of sine, we give its own name because putting a -1 on it would be confusing. So if it's a number with a -1, that's reciprocal. If it's a function with a -1, that is an inverse. And it's that process of an inverse is x and y switch places. All right, so using some of these rules, I'll try and keep them up there. If I have x cubed times x to the 4th, never mind, I can't keep them up there. That screen is getting too small. X cubed times x to the 4th. What does that simplify down to? X to the 7th. Add them together. X squared over x cubed. X to the 2 minus 3. What is 2 minus 3? -1. If you were told do not have negative exponents, what would this also be?
1 over x.
1 over x. Great. 3 to the x cubed. That simplify with? How could I get rid of the parentheses? Yeah, I'm hearing 3 to the 3x. And we could actually simplify this more because that changing this to multiplication actually does mean I can kind of switch what the exponent is. So if I wanted to simplify this even more, say I'm needing to get x by itself, this could be thought of as 3 cubed to the x. And what is 3 cubed? 27 to the x. So, power of a power and ultimately end up switching those orders. And last one here, 1/3 to the negative x. Just 3?
3 over x.
I'm hearing something with an x. The exponent itself stays the same, just changes signs. The negative flips it, then the exponent stays the same, other than the sign changes. So 3 to the x is what we'll have. Right. So let's look at what do these graphs look like in general with the finger maybe. What would a general exponential graph, I just said, what does an exponential graph look like? You want to know the basic shape. Yeah, just any exponential has a basic shape to it. It, trying to get you guys in the right, we will graph these specific ones, but the general shape of just any exponential is it starts off growing slow and picks up real fast and grows exponentially. Hence the name exponential function. Grows really fast. If I wanted to graph specific ones without a calculator, could plot some points. So say we are doing f of x equals 2 to the x. We have, if I plug in my x values here and get our y values. If I plug in 0, what is 2 to the 0? 1. If I plug in 1, what would be 2 to the first?
2.
2. If I plug in 2, 4, 3, 8. So plotting those points. 7 is where that ends. If I plugged in -1, what would we get? A half. So I'll get these as close as I can. I'm not going to get them perfectly. -2, 2 to the -2. 1 over 4 would be 1 over 2 squared. Exponent stays the same. 1 over 4 is what that 2 squared would simplify down to. So we have 1 over 4. And maybe seeing a pattern. 2 to the -3. 1 over 8. Hopefully noticing the denominators with how a negative flips a fraction. Negative exponent flips a fraction. So with a little bit more precision, I say, as I'm surely about to botch this function, we have the exponential, man, it was wrong. Yeah, look at this again. We have the exponential function starting off growing really slow and then growing really fast, keeps on going forever and ever, amen. Keeps on growing. On the same graph, I'm going to remove these. I'm going to look at the g of x function. G of x equals 1/2 to the x. I'm going to, here is my g of x. I'll rename that Lu1f of x here. All right. If I have 1/2 to the 0, what would that be? 1. If I had 1/2 to the first, 1/2. So I'll fill in those. We have 1, 1/2, 1/2 squared, 1/4. And what do you think about 1/2 cubed? 1/8. So we have 1/2, 1/4, 1/8. And then 1/2 to the -1. 2 flips the fraction. 1/2 to the -2. 4 flips the fraction. 2 to the 4, 2 squared is 4. And 1/2 to the -2. Oh, sorry, did I say it? 1/2 to the -3 is what I was meaning to say. I don't know what I said. 8 flips the fraction. 2 cubed is 8. what? Let me plot those points in. What do we notice? Assuming I can actually hit these points as well as possible about these two functions, how they're related to each other. Not inverse.
Symmetrical.
They're symmetric to what?
Reflection.
Yeah, they're a reflection over the y-axis. If I had rules, how we talked about the rules, how do I flip something or reflect over the over the y-axis? You make x negative. If I have my function, I make x negative. That will flip it over the y-axis. If that comes out to be the same original function, that was what we call an even function. These are not the same function, but they are reflections of each other over the y-axis. Well, that means f of x was 2 to the x. If I want to reflect it over the x-axis, the y-axis, I make x negative. Reflect would be make x negative. I'll give it a new name. No, I'll keep it the same. F of negative x equals 2 to the negative x. And what does a negative do? It takes the reciprocal of the number, which is 1/2 to the x. That was our g of x function. So the fact those are reflections is not a surprising fact. It is coming from this rule about flipping over the y-axis or reflecting over the y-axis. Make the x coordinate negative. We're not going to look at the 3 to the x. It's the exact same. Well, what do you think would change with how quickly it grows in the 3 to the x? Is it going to, it's going to have the same general slope or shape, is what I want. Is it going to be on this side above the blue or below the blue? Gonna be above, because 3 to the first would be 3. 3 squared would be 9, and there is why we're not going to graph all of it. There's not a whole lot of points we can do. And we'd also have the opposite over here, where we would be below the blue, because 1/3 and 1/9 get smaller than 1/2 and 1/4. So we have those general properties. So some properties of the exponential function. F of x equals a to the x, or g of x equals a to the negative x, which is just, hey, I can raise it to a negative exponent and I still get an exponential function. Where a is a real number that is greater than 1. So this is the ones that have the shape of the 2 to the x. And these ones have the shape of the 1/2 to the x. So the difference in those are just saying, do I grow on the right hand side or on the left hand side? F and G, they both have the domain negative infinity to infinity. I can plug in any number to an exponential. They have the range 0 to infinity. And I want to note this symbol. Can I get 0 out of an exponential? Is there any x value so that e to the x equals 0? would I be able to get an X value for that? What does a parenthesis mean when it comes to domains and ranges? Can I include that value? No. The parenthesis means that value is not included. And so what that means is e to the x equals 0 doesn't have a solution. There is not an x value I can put in to get 0. So there is no solution to e to the x equals 0. The graphs of f and g each have a y-intercept at 0, 1. Hey, that was part of the reflection thing we saw here. They both crossed through 0, 1. Big part of that is due to the fact that exponential functions have the property that any number to the 0 is 1. And f and g are 1 to 1. If they are 1 to 1, what does that mean they have? So there's a property of something necessary that we talked about last. They have an inverse. Yes. They have inverses. They are not inverses of each other, but they have an inverse. Inverses. As we saw, they reflect over the y-axis, but they don't have that inverse function property of the graphs that I will review in a little bit. All right, with calculator, I want you guys to try filling in this chart. So we have the function 1 plus 1 over x all to the x. I want you guys to try plugging in 1, 2, 10, 100, 1,000, and 10,000. If you got a calculator, you should hopefully have a calculator. Phone calculator works as well. See what values you get when you plug in these x values in to the function. Give you guys a little bit of time to try that. Yes, it's going to be decimals. Yes. Is what I'll ask you guys. Give me. So what do we get if we plug 1 into those x's? We have 1 plus 1 over 1, which is 2, all to the first. 2 to the first would be 2. What do we get if we plug in 2? Maybe we work this together. I'm going to pull up a TI to show a nice way to do this. Okay. We could plug them in one by one. I'm trying to get rid of some ads before I share my screen again. I can get rid of said ads. Yay, free calculators.
There's one built into the computer. Not sure if it'd be completely CI though.
Yeah, I know there's the little calculator that I can pull up quickly, but I don't fully know how to work that as well. And also I don't know if it will be able to do the things I want to right here. So I'm gonna type that function in. 1 plus 1 over x. Nope. That is the one problem with this. Is that the button for x is not x to the x. Okay. Then I'm gonna go to table set and change it to have me. It's gonna ask me to put in the independent variable. It's gonna ask me to put in the x's, and then I can go to table and put in x. If I plug in 1 to y1, I get 2. If I plug in 2, I should get 2.25. That would be 3/2 squared, or 9/4. 2.25 is 9/4. The rest of these cannot describe the mental math on them. The next one I asked for was 10. Should get 2.5937. You'd have 1 plus a tenth, or 11/10 raised to the 10th, which is not something I can do in my head. 100, 2.704, or 2.70 is what I'll have written. 1,000, 2.7169, or 2.717. I'm gonna have to fix that one. And 10,000, 2.718. So this one was actually 17, was how it rounded. Are those decimals recognizable to anyone? Specifically as we're getting this out here. Specifically if it rounded to like 2.72 something.
They're getting closer and closer to the same number.
They are getting closer and closer to the same number. Actually, no, it's not 2.72. That is the rounded value. They're getting closer and closer to the same number. And particularly that number is a very important one in math in general, in most sciences, if not all. It's E. This is getting closer and closer to E. With some notation we'll talk about later this week. This is saying, as I make my x bigger and bigger and bigger and bigger, 1 plus 1 over x gets closer and closer and closer to the value of E, which is approximately 2.718. 2818286 was how many decimals I copied down. It keeps going. It is irrational, like pi. It is known as Euler's constant, is its official name. Euler's name starts with the letter E. But what it is this very unique number where a lot of things end up converging to it, and we'll see some really cool properties about it as we progress. But there is a natural exponential function, and that would be that function e to the x is known as the natural exponential function. E has, like I said, some really nice things about it, and it comes up almost at the most random times. But one, looking at something like this, where I'm making this fraction, what this means is this fraction, the denominator gets bigger and bigger and bigger. If I have a fraction getting bigger and the denominator gets bigger and bigger and bigger, like 1/2, 1/3, 1/4, 1/5. What do those fractions get closer and closer and closer to? 0. So this fraction here gets really close to 0. And this is saying 1 plus something really close to 0 raised to essentially as big of an exponent as possible. We know the number that comes out to, and it's 2.718 blah 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 e. So like I said, it's irrational like pi. One place it comes up a lot is this formula. If you've worked with compound interest type formula things of something compounding over time continuously, or not continuously, but something compounding over time, that's what this formula looks like. And if at any point you have learned that your interest, nope, that's not what I want. If you have a compounding continuously formula, your like if a loan compounds continuously, like every second more interest is being applied to your loan, may have seen the principal times e to the rate of interest times t formula. Maybe it's been called PERT. What is the letter I'm looking for that this is equal to? This is basically how much debt you have at some amount t. So I'm going to just call it d of t. E here that comes up is this constant. So what is E? It's this idea of when we compound some percentage over and over, we get this constant E. And it's this very weird, mind-boggling thing of 1 to something that's really close to 1 raised to a very large exponent. We know the number it comes out to. But it is the big part here is it's the natural exponential function. It's the main one we'll go back to. Natural exponential function. And it's related to something we're going to use a lot as well. And you've probably seen used a lot. So the graph of e to the x, because there are decimals, I'm just going to go through and plot them. But first, if x is 0, what is e to the 0? 1. That one we can do. E is 2.17 or 71. Yeah. It's somewhere in there. If I plug in 2, I get e squared, which is that is above 7. That is 8 something. The plot would be up here. It will have, the whole point of this statement is it will have this very common shape. The graph of e to the x is going to have that exponential shape. It has an inverse. That was the whole point of saying up here somewhere. It's 1 to 1. It has an inverse. if I gave the equation, say 5 equals e to the x. I don't know how to solve for x there. Anyone seen these types of equations before? How we get e by itself?
I didn't even know E existed till 5
Okay,
minutes ago.
that's okay. Well,
That's fun.
yeah, well, anyone seen it before and know how to get e by itself?
They have all like a square root. Probably.
It's gonna have something like a square root. Anyone? Why are the ads back? Okay. So on here, on your calculator, pointing to the logic behind how buttons are placed. There is a button that has that e to the x. I'll also say, as far as e being a special number, it also exists as its own button under pi. And I said e and pi are very similar. E to the x, another button over here. We're talking about the function e to the x. This button here, ln, stands for the natural log. The natural log is the inverse of e to the x. So the natural log is the inverse of e to the x. And the natural logarithmic function, let x be a positive real number, the natural logarithmic function, denoted by ln of x, it's a function, x is the input, is defined by ln of x equals b if and only if e to the b equals x. It's this weird way of rewriting things for the idea of solving or flipping x and y. So if I know ln x equals b, I will take my x and set it equal over here. I will take my b and raise it to e. And that is how I can rearrange equations. So like e to the 0 equals 1. E to the 0 equals 1. Using this one I just circled form, what is in the spot of b? What is in the spot of x? So I can rewrite it to say the natural log of 1 is 0. Let me go to a calculator, prove that point. If I type in, using my calculator, hit that ln button, 1, close my parenthesis, we had better get 0 back, and sure enough we do. The natural log of 1 is 0 because e to the 0 is 1. It switches that 1 and the 0 and changes some notation. E to the 1 equals e. What is in the spot of b on this? 1. What's in the spot of x? E. So this is saying the natural log of e is 1. Calculator, is that true? Natural log, second e is 1. They are undoing each other. Natural log and e cancel each other out. It would be like, if you see natural log of e in an equation, that is like saying 2 times a half. They cancel each other out. And then this last one, what is in the spot of b? -1. What is in the spot of x? 1 over e. This is saying the natural log of 1 over e is -1. It's flipping things around. Again, checking that with the calculator. 1 over second e -1. They are inverses. The last one, e to the ln of x is x. This is that composition rule of inverses. But if I want to write this as a logarithmic form, b is the natural log of x is x. And so rearranging it would say the natural log of x equals the natural log of x. That feels like probably the most, two things that look exactly the same are equal. Feels like the most. Did we really write those two things are equal statement? Yes, but it is saying these are inverses of each other. E to the x and the natural log of x are inverses. Property, we'll come back to the properties real fast. E to the x looks, nope, it grows faster than that. So let's put that in. E to the x, no, gonna try that one more time because I really want to go through this point, but otherwise, this will be my last attempt at the graph of natural log. Okay. Here is the graph of e to the x, as precisely as I care about right now. We had on Friday a property for inverse functions. What did inverse functions reflect over? Like they were reflections of each other over a particular line. Yeah, the x equals y line. So here is that line being put in to the best of my quick ability. If I reflect this red line, e to the x, over that green line, y equals x, I'm going to get the natural log, which means the natural log looks something like that. The natural log grows really fast and then tapers off. Using our properties of inverses, inverse functions, the domain and range flip. So the domain of the exponential was negative infinity to infinity. So the range of natural log is negative infinity to infinity. The domain and range flipped. The range of e to the x was 0 to infinity. So the domain of ln of x is 0 to infinity. These flipped from that previous chart we looked at. The other chart said the y-intercept of e to the x is 0, 1. So the x-intercept of the natural log goes through 1, 0. That is the 1 point that flipped spots. 0, 1 became 1, 0. And it is also 1 to 1. It has an inverse, and that inverse is e to the x. So e to the x and the natural log of x are inverses of each other. We get properties of logarithms, or the natural log, that go hand in hand with our properties of exponents. So we had the rule that e to the x, e to the y would equal, or let me use a's. A to the x a to the y equals a to the x plus y. We have the same thing happening with logarithms. If I have a product inside a logarithm, I can expand it out to be a natural log of one thing plus a natural log of another. So it's undoing this multiplication rule. Division, when we previously subtracted exponents, now if I have a division, I can subtract the logarithms. One way to think about logarithms based on this rule, where was it? Rule 4. Logarithms, in the back of our mind, they are exponents in disguise. It's like we've looked at an exponent by itself. So if I was just looking at those exponents by themselves, we're getting these rules. And then one of the biggest ones, if I have the natural log of x to the z, so inside a natural log I have a power, I can bring that power down. We're going to see that one play out a few different times. So, we want to expand using those rules. This time I will try and keep them up there. I have a division. Rule 2 tells us I can expand that out to be subtraction. The natural log of 10/9 is the same as the natural log of 10 minus the natural log of 9. Looking at 2, the square root. Is there another way I can write the square root with an exponent? A power of a half. Okay, so rule 3 tells us if I have this exponent, it will be the same as bringing it down as 1/2 times the natural log of 3x plus 2. Now, do I have any rule about a plus inside of the natural log? So anything in the left-hand column? No, there's no plus rule there. So there's nothing more I can do. The only thing I can do is bring down that 1/2. Okay, the last, nope, we've got 2 more. Natural log of 6x over 5. What is being done inside the natural log? Well, what do we visibly see? What is a division? Division turns into what by these 3 rules? Subtraction. So I'd have ln of what? 6x minus ln of 5. Is there anything else I could do to expand this out? There is one more thing. I will say there is one. I have a product right here. 6 times x. What happens to a product inside the natural log? It turns into addition by the first rule. So this would be the natural log of 6 plus the natural log of x minus the natural log of 5. And the last one, I'm going to zoom in and I will walk through them. First, the big thing I see is division. So I'm going to separate these out with division of ln x squared plus 3 squared minus ln of x cubed square root x squared plus 1. One clarification here. I said x cubed. That is a cube root, not an x cubed. So I'm just going to move that 3 just a little bit here. just to reflect that. So it's x times the cube root of x squared plus 1. Then it would be each one individually. I have an exponent. What happens with an exponent? Comes down in front. Here, the big thing I have happening is a product. A product would turn into addition. So ln x plus ln. I'm going to rewrite the cube root as what would be an exponent of a cube root? 1/3. And the last thing that can do is addition. I can't split apart an addition inside. That's as simple as that can be. This is an addition inside, but it has an exponent, so the 1/3 can come down in front of the natural log it's immediately on. X squared plus 3 minus ln x plus 1/3 ln x squared plus. Right. We can also go backwards. So I want to add one problem of if it says condense or combine, we can go backwards on these. So that would be things like ln of x plus ln of 2 to the 3rd. No. We'll see. I'm gonna change that back. 3 ln 2. Okay. Minus ln of 7. I can use these rules to go backwards. So the one that I move, I can bring that 3 back up. This would be ln of x plus ln of 2 cubed minus ln of 7. If I have them expanded out addition, I want to condense it down to a single natural log. Addition would turn into multiplication. And subtraction would be division. So I'd have ln. I'm going to turn this 2 cubed into an 8. Minus ln of 7 is ln of 8x over 7. So depending on the instructions, if it says expand, it's using the rules to make it as long as possible. If it says write it as a single logarithm or condense, it's the try to get it down to the point of having only one natural log. Now, the big thing for these problems is the fact E and natural log are inverses. So if I want to solve for x and I have an E or I have a natural log, I'm going to be using E and the natural log to cancel each other out. So I have an E. What cancels out an E? A natural log. So just like with all of our algebra stuff, what we do to one side, we do to the other. So I want to get rid of this E. So I'm going to apply the natural log to have E to the x plus 1. What I do to one side, I do to the other. What can I do with an exponent that's inside a natural log? Put it down in front. So I'd have ln of 7 equals the whole exponent comes down to be x plus 1 times the natural log of E. What is the natural log of E? 1. Why does my computer do this? It seems to only be this room as well. Where was it? It was a property somewhere. It's here, first of all, kind of. Right there. The natural log of e is 1. You see that? That cancels. That goes away. So I have the natural log of e is 1, meaning ln of 7 equals x plus 1. Oh, would we get x by itself?
Subtract both sides by 1.
Subtract both sides by 1. So ln of 7 minus 1 is x. Okay. ln of 7 being a function means I am taking 7 and putting it into that function and getting a number. Natural log, pi, all those things often seem a little scary sometimes. But if I have natural log of a number, that is just a number. I can put that into my calculator and get a number. So where did my calculator go? There it is. The natural log of 7 is a number, and in particular, it's the number 1.9459 blah, blah, blah. But it is a number, so I can subtract 1 from it just like any other number. 1.9 minus 1 is that 0.9. So x is approximately 0.946. 0.946, and we have that solution. Looking at in the other way, I have a natural log. What cancels a natural log? E. How we cancel a natural log here is this idea of we're going to make everything a power of e. I made a comment earlier of natural logs are exponents in disguise. I'm going to make that natural log an exponent by saying e to that thing. So e to the natural log of 2x minus 3. What I do to one side, I do to the other. So what would I have on the other side?
E to the 5th.
E to the 5th. E and the natural log cancel each other out, leaving us with just what's inside that exponent. If we go back, yeah, the 2x minus 3 is e to the 5th. E to the 5th is a number. We can type that into our calculator and get a number. So how would I get x by itself? Add 3 and divide by 2. So x is e to the 5th plus 3 all over 2. Which in our calculator, I'm going to use the e to the x button here. I'm going to put in a parenthesis first. E to the x, it gives me that spot to type my 5. I need to arrow over to bring me back down. Plus 3 divided by 2. 75.707. This is approximately 75.707. In ideas of different wording, like with radians, we work with pi in our answer as much as we can, but sometimes we have to get a decimal approximation. If you're asked for an exact answer, that would be this thing. If you're asked for the decimal approximation, that would be this part. If you're asked to show the steps of isolating x, that's this part. So e and natural log cancel each other out, and so they end up going back and forth. I want to look at a couple more. Let me actually just pull some rather than try and make any up. Very far back here. 1.6. Okay. Let's try. I like that one. I might have assigned that one. That's okay. ln 3x plus ln 2 equals 4. And we're also going to look at, if it's the same problem, I don't care. That one. We'll do one with a natural log and one with an e. So the two problems we had, the natural log and the e were the first immediate thing. What I mean by that was we had, on one side, all we had was an e to an exponent, right? There's nothing else going on the right-hand side other than e to an exponent. And on the second one, nothing going on except the natural log of something in parentheses on the left. If I have more going on, I want to get a natural log all by itself or an e all by itself on one side. So looking at this natural log one first, I have two natural logs. I'd really like to combine them into one. How could I combine those into one? Turn it into a multiplication. So what is 3x times 2? Now I have a natural log all by itself on one side. I have the natural log of 6x. How do I get that natural log to go away? E, specifically, how am I going to write this? What are these going to become is what I kind of mean. They're going to become exponents. So e to the ln of 6x equals e to the fourth. E to the fourth is a number. There is no x over there. It is just a number. So what does that simplify currently down to? What cancels out? ln and e. So I get 6x is e to the fourth. How do I get x by itself? Divide by 6. E to the fourth over 6. We can get that in a calculator. Might as well. To see that is a number, we can get that number. E to the fourth divided by 6. 9.099 is what's going to solve that equation. Second one is e all by itself. Do I only have this e to the x on this side, or do I have more going on than that? Have more. So when I have things like this, and even with the natural logs, think about in terms of how would you solve 8x minus 12 equals 7? Add 12 to the other side, then divide by 8. Same thing. I want to get my e to the x by itself. I add 12 to the other side and divide by 8. So 8 e to the x equals 7 plus 12. I copied this right? Not that that's a problem. No, that's not a problem. Just wanted to make sure it wasn't divisible by 8. It's not. That's okay. We have calculators. Divide by 8. E to the x is 19 over 8. How do I get x by itself? Natural log. How do I get x all by itself? I get rid of e by taking the natural log. I'll write out everything here of we'd have the natural log of e to the x equals natural log of 19/8 what cancels? E and natural log, which it really cancels after I'm bringing this x down to have x ln of e, but x ln of e is 1, so I have x equals the natural log of 19/8. Which is 0.864, 0.865. Want to give one last mental check of things to watch out for. If you get to the point of having a negative inside your natural log, that is a good point to go, I might have done something wrong. Because what I had written, natural log of -5, if I try to do that, I get an error. That is because of the domain of natural log. The domain is from 0 to infinity. Can I plug 0 in? Can I get the natural log of 0? No, because of the parenthesis, I can't plug 0 in. So natural log of 0 doesn't exist. Natural log of a negative number doesn't exist. So that is, at least at this point, a good check. If you have natural log of a negative number, you might have done some algebra wrong somewhere. If there's an x inside, a negative is okay because x can be a negative and cancel it out. But I'm saying a negative strictly number, no x's in sight, can't happen.
So what if there's a 0 then?
Natural log of 0, also probably did something wrong. We'll talk about limits of that, but at this point, if you get natural log of a number that is 0 or negative, your calculator will yell at you.
Oh,
Yeah.
I was thinking if 0 would just count as 0, or if it would also be an error.
It would also be an error. We can actually see that real fast. Second quit. Natural log of 0. Error. Is there a hand back there?
Yeah,
Yeah.
So when we're working in radians, we never use pi as an actual number, but here we always do. The natural, like when we have, I guess 4/3 pi, we never enter that into the calculation, right?
Yeah. So that was my comment of you're going to see a lot of instructions that say round your answer to 3 decimal places. So it is type it in, but if you see the words give an exact value, which is probably what I would look for more on exams. The idea is if you do the work right, you should be able to say, here is the exact, but then ultimately these do come up a lot in science, so it is one of those, we do want those decimals. Pi, yes, pi, leave pi. These follow the instructions. But you should also be showing your work as to how you got it. Please never just give me 3 decimals and go, you just asked for 3 decimals. Show how you got there. Yeah. The work is the more important part, ultimately, at the end of the day. All right. I think I've closed my announcements. So you have a post-class discussion, which is not discussion, activity. That is a problem similar to those last ones we did. I don't remember if it was E or natural log, but it was similar to these problems. That will be due Wednesday. If you have any questions on the homework you got back, let me know. Or if you have any other questions, let me know. Have a great couple of days. See you Wednesday.